Welcome to lecture number 17 for ECE476 Advanced Embedded Systems. In this lecture, we're looking at timer interrupts using a Raspberry Pi Pico and Python. So, recapping, in the previous lecture, we covered edge interrupts. Edge interrupts are subroutines called by hardware, and the hardware subroutine can be triggered based upon a rising edge or falling edge or both edges. In this lecture, we're looking at timer interrupts. That's a subroutine that can be called every n seconds for a periodic interrupt, or triggered n seconds in the future for a one-shot. Now, timer interrupts are also useful. They can make your code more efficient and accurate, basically a more efficient and accurate version of the sleep command. You can have more precise timing in the main loop, and your processor isn't shut down like the sleep command. It can be doing other things while you're waiting for that much time to elapse. And with timer interrupts, you can build an automated stoplight, you can sample voltage every n milliseconds, or implement a digital filter. So we'll look at all those during this lecture. So in this lecture, we're going to go over what timer interrupts are, how they're set up, and some things you can do with them, such as I can implement a t-on function. An event won't happen until I hold the button down for, say, 5 seconds. Like if you want to make sure that the person really wants the motor to turn on, you got to hold the button on for 5 seconds. I'll implement a t-off function. When I turn off something, it'll hold for like 5 seconds, like a bathroom fan. I want the fan to keep on running for, say, 5 seconds after the light turns off. I can do more accurate timing for a stoplight. And I can set up the timing for a game of Hungry Hungry Hippo to make it 10 seconds dead on. And one thing to note, interrupts do not interfere with each other, so I can't have timer interrupts, I can have edge interrupts all running at the same time. They don't conflict. So let's start out with the kind of most basic timer interrupt. Suppose I want it to interrupt every 1 second. Well, the way I do that is use the time initialize. In this case, I'm going to include the timer function for machine. I'm going to define it to be every 1 second. I'm going to trigger the interrupt. It's going to happen over and over again. That is periodic. And when it happens, I'll call the subroutine tick. Then every second, this subroutine is called, that's triggered by hardware. It's going to pass data to the main routine through a global variable. And the main routine just displays what's happening. So to see that happen, let's go to Python or Thonny. Here is a 1 second counter. The interrupt is called every 1 second. It sets a flag. When the flag is set, it prints what's happening. So if I stop the code and restart it, it starts out at 1, and every second, the main routine counts. So this is my 1 second counter. Much more efficient. The main routine can do whatever you want. Every second, the flag is set, and that'll tell the main routine to do something. In this case, it's just going to print. In terms of program description, what triggers the timer interrupt is this command right here. That sets it up for 1 hertz, happens over and over again, and there's the subroutine call. I can change that. Like suppose I want this to be every 2 hertz. So every 2 hertz it's going to count. There's counting every 2 hertz. And this doesn't have to be an integer. 2.32146. Happens over and over again. Now there's periodic and one-shot. What a one-shot does is it'll call the interrupt just once. So I call it there. Where I would use that is, suppose I want this to be, say 5 seconds in the future. So when this is called, 5 seconds from now, the subroutine is going to be called. It then sets the flag, and the main routine clears it. So I set go, wait 5 seconds, 2, 3, 4, 5. There it is. The subroutine was called just once. That's a one-shot. Second example of stuff you can do with a timer interrupt. I can do a fire cheat. So this would be like for a video game. When I press a button, I want it to shoot off 3 rounds. And I can make these almost as fast as I want. For this example, I'm going to have every 200 milliseconds, I toggle. In this case, it gives me 3 toggles every button push. I can rattle off 3 shots when everyone else is just rattling off 1. That's a fire control cheat. So to do that, I am going to have a falling edge interrupt, like we did in the last lecture. That's the part in blue. When I press the button, it triggers the subroutine fire. Fire then sets up a counter. If n is equal to 0, it resets it to 5. That's how many toggles I'm going to get. I'm going to set a flag. That's just so the main routine can see what's happening. And then set up a timer interrupt. There's periodic. So it's going to rattle off at 5 Hertz every 200 milliseconds a toggle. In Thonny, I can try that. So to see how that works, here we have the code in Thonny. When I hit the button, it's going to trigger a falling edge interrupt, sets up my counter to 5, sets the LED, and then for 5 edges at 5 Hertz, it's going to call tick and toggle the pin. So here if I do that, push, you see GP16, press. Actually helps to run the code first. So when I run it and press the button, it displays the counter. So set clear, 3 shots. If I zoom in on that, I can see button 16, 1, 2, 3, 3 shots. 1, 2, 3. And if I want to speed it up a little bit, let's do shots at 20 Hertz. Probably harder to see, but if I run that, blip, 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 blip. I'm not sure the camera can pick that up, but see, I got 3 little blips really quick. That's a fire control cheat. Another thing you can do with timer interrupts, I can do things like a bathroom fan and light. There's a T-off and T-on function, something that's common with ladder logic. With the bathroom light, I'll have 2 buttons, an on button and an off button. When I hit the on button, the light and fan turn on. When I hit the off button, the light turns off, but the fan turns off 5 seconds later. So come up with a function that does that. Well, here's one program. I'm going to set up the 2 pins for on and off. When I hit the first button, I call the subroutine on. That turns the LED on, the fan on. The second one is off. When I hit off, I'm going to turn off the LED and turn on a timer interrupt for 5 seconds in the future. That's a 1 shot. That timer interrupt will then turn off the fan. So if I run that, here's kind of what happens. I hit the on button, the light and the fan both turn on. Hit the off button, the light turns off right away. 5 seconds later, the fan turns off. Again, turns on both at the same time. 1001, 1002, 1003, 1004, 1005. Fan turns off. I can do a T-on function. What the T-on function is for is sometimes if I just bump a button, I don't want to necessarily turn on the motor or heater. I've got to hold it down for 5 seconds to really make certain I want to turn this on. That's the T-on function. So what I should have is, like on this pin, as I just tap it, it ignores me. I've got to hold it down for 5 seconds, then it turns on the motor. As soon as I turn it off, it turns off right away. And Thonny, I can do that. Here's a T-on function. When I press the pin, that calls I've got a 10 second or 10 Hertz timer. When I hold the button down, it's going to turn on well, check. Hold the buttons down, I'm going to increase the counter. If I get to 5, I turn on the light. So if I try that, here's my counter. I hold the button down, you can see there's my running time. If I get to 50, the light turns on. Release the button, turns off. So over here, kind of see that. Hold the button down, 1, 2, 3, 4, 5. Light turns on, otherwise turns off. Oh, stays on. Here's the off button. 1, 2, 3, 4, 5. Turns on, off. And if I hit it for shorter durations, as soon as I release the button, it clears out. So that's one way to do it. Second way to do it is have an edge interrupt on the rising edge or falling edge. When I press or release the button, I'm going to call light. If I press the button, it's going to turn on, call the subroutine light on, in 5 seconds from now as a one shot. If it's a falling edge interrupt, I'll turn the light off. On light off, I turn the light off. On light on, it turns on. So this is kind of the same thing. You don't really see the time being counted. That's kind of done internally. So over here, if I hold the button down, this is kind of just counting over here. If I get to 5 seconds, the light turns on, turn it off. There's my counter. It's going to wait until I get to 5 seconds. If I hold it down for 5 seconds, the light turns on. And it stays on until I turn it off. That's a second way of doing it. Probably a little bit better way to do it because I'm just don't have to sit there and constantly pull. I'm using a one-shot. You can see over here. I'm using a one-shot to turn the light on or off. It's going to be turned off and turned on in 5 seconds. If I release, it's going to be turned off in 200 milliseconds at 5 hertz. That's the T-on function. Another example, we can play Hungry Hungry Hippo more efficiently. In this case, I'm going to have a couple different interrupts running. I'm going to have edge interrupts keeping track of the games. I'll have the game start. That sets up 10 seconds. And then the game will run for 10 seconds flat. So in terms of coding, I'm going to have a couple input pins. This starts the game, plays the game. Once the game starts, it sets to 10 seconds or 1,000 counts at 10 milliseconds per count. I'll set up the different pins for interrupts. I've got the game start, sets the game to 10 seconds. Player 1 counts player 1, player 2 counts player 2, as long as the game is on. I'll have the timer. At 100 hertz or 10 milliseconds, I'm going to decrement the time till it gets to 0 and toggle an LED just so I can tell what's going on. Then the main loop doesn't really do anything other than display what's going on. Now the advantage of this approach is previously the Hungry Hungry Hippo game was a little bit off in timing. This one ought to be dead on. So go over to Hungry Hippo. Again, I've got the 2 push buttons. As long as the game is on, I'm toggling it so here you can see the game is actually running for 10 seconds. I start the game, there's my time in seconds. I hit the different player buttons, the score goes up, some bouncing. Then the game's over once you get to 10 seconds. Now this is a better way of doing it. Previously the timing was a little bit off. That's because I had a sleep statement and the total time was the time of the main loop plus the sleep. Here I don't have to do that. The time is tracked using interrupts. So the game is just dead on 10 seconds. Once the game's over, it quits recording. I have an improved Hungry Hungry Hippo game. I can do an improved stoplight. So interrupts are much better, much more accurate way of keeping track of time. It doesn't care how long the LCD routine takes, it'll still be accurate. So if I want to do a stoplight, what I could do is just have a counter. I'm going to have the green light is on for 5 seconds, then yellow, then red, then green, yellow, red, and so on. I'm going to have a counter. As I count, I'm going to count 0, 1, 2, 3, 4, 5, repeat. That tells you what color the lights ought to be. To do that, what I'm going to do is set up timer interrupts as one-shots. If I'm in state 0, then in 5 seconds, I'll call an interrupt, go to state 1. If I'm in state 1, in 2 seconds, I'll call the interrupt, go to state 2, and so on. So it keeps on repeating. And that's what's happening here. In Thani, you can see the different counters. It's displaying the time every 0.1 second. And in the background, the counter N is changing. Based upon N, I'll tell you which light color it ought to be. And the net result is it's 2 seconds, state 5, state 0 for 5 seconds, state 1 for 2 seconds, state 3, 0, 1, 2, 3, 4, 5 for 2 seconds. I have a stoplight, and the timing is much more accurate. I don't have to rely on pushing the button. The timer interrupt is changing N. I could add a walk button. So normally the light is green. If I hit button 15, it'll wait and then go through the light sequence. So go over to stoplight 4. And now what's happening in stoplight 4 is I'm waiting for a button to be pushed. Let's see, where is it? When I hit the button, it starts up my 10-second timer. That's my timer right there. Then I go through the different light sequences. And what's happening is I'm setting up tick to be 10 Hertz. At 10 Hertz, I'm going to count. And based upon the time, that tells me what N should be. Then the main routine, based upon N, displays the colors. So here I'm waiting for the walk button. Waiting. Hit the walk button. In 10 seconds, the light will change. Goes to yellow, red, goes through the whole sequence. When I get back to green light, meaning don't walk, it's now waiting for the button push. Once I push that, that'll start the 10-second sequence and turn on the tick. That's what's happening with the walk button. When I hit that, that triggers a walk in 5 seconds. The walk subroutine, when I hit the button, that's an edge interrupt, triggers the walk. That turns on the stoplight subroutine. That's got the counter. Another example of things you can do with timer interrupts. I can have a more precise measuring of time. So for example, I want to measure the RC time constant of a capacitor. What I could do is set up the interrupt for every 1 millisecond, If I use time.sleep, it isn't exactly right because the main routine is going to be a little bit off. If I try that, for example, here I'm using a sleep interrupt. The frequency is 568 Hertz, which means the time is 1.7 milliseconds. The sleep is right here. That's your 1 millisecond. Plus everything else takes a little bit of time. That's the A to D reads, etc. So my sampling rate is wrong. If I have wrong sampling rates, my data is bad. A better solution is to set up timer interrupts, where I interrupt every 1 millisecond. If I do that, I'll be calling the subroutine every millisecond. I'll be measuring your analog input. And note here the time is actually 1 millisecond. So here's what the code looks like. I've got the interrupt right here. The tick at 1 kilohertz every millisecond. This is called it sets a flag. The main routine then waits for the flag to get set. Once it's set, it clears the flag, runs through the whole routine, and if you display the LED, it's precisely 1 millisecond. Now when it's 0, I'm waiting for the interrupt for 1 millisecond to elapse. When it's 1, I'm doing stuff. So as long as everything else I'm doing takes less than 1 millisecond, I'll have a 1 millisecond sampling rate. And with that, I can do things like measure the RC time constant. So here's the trick. The display routine is actually going to be fairly slow. So what I'm going to do is initialize my vectors. I'm going to collect 1,000 data points for X, the input voltage, a square wave, and the output voltage. I've got 2 different interrupts at 2 Hertz, actually 10 Hertz. I'm going to be toggling the output pin that generates the square wave. Then I've got, over here, a RC combination. I want to measure the capacitor charging and discharging. I'll measure that at 5,000 Hertz. Pick your sampling rate. At 1,000 Hertz. At 1,000 Hertz, fill up my buffer. That'll take 1 second. Once the buffer's full, here for 1,000 points, I wait for the flag to get set. Once it's set, start triggering. That sets my sampling rate to 1 millisecond. Collect your data and repeat. After 1,000 data points, display your data. So here's what that looks like. If I want to slow down the square wave, it seems a little bit fast. So let's make the square wave, instead of 10 Hertz, let's make it 2 Hertz. So there's your square wave, and there's your RC time constant. It then collects another 1,000 data points, then plots it. Wire in the way. I can collect data, and we'll be doing this a little bit later as well. To use the data, what I'm doing here is I'm plotting it. What you could also do is do a print command, and they'll print out over here 1,000 data points, which you can then import into MATLAB, plot some other way. Finally, I can build a digital filter. Anything I can do in software, I can do in hardware, and vice versa. So here, this is a hardware solution. I have an RC filter. So here's the output. Goes through a resistor, goes to capacitor. Simple RC low-pass filter. I can do other types of filters. When I do that, I get this kind of response. There's your capacitor charging, discharging, and pretty clean data. Anything I can do in hardware, I can do in software. In software, I actually want to implement it using Z-transforms. So suppose I want to implement this filter. That's a second-order Butterworth low-pass filter. Poles are at -5 plus minus J5. Here's the transfer function. A little bit harder to do in software. If I convert to the Z-plane, that makes it fairly easy to do. I convert as Z is e to the st. So here's the poles in the S-plane, poles in the Z-plane. There's your poles. Multiply it all out. Here's my transfer function. And code. That's basically your code. This is the denominator polynomial. Solve, I get z squared y. That's the current value. 1.9y, bring it right. So current value of output is 1.9 times the previous output minus 0.9, output 2 samples ago, plus 0.0012 times the input, plus twice the input 1 sample ago, plus the input 2 samples ago. Each decreasing power of z is a delay. So the code is basically this part. I'm going to remember the input, previous input, input 2 samples ago. Here's the output, output 1 sample ago, output 2 samples ago. Do this every millisecond. I've implemented the filter in software. So in Thonny, what I would do is, here's my digital filter. I'm going to wait for the flag to get set. That's every 1 millisecond. Keep track of the current input, what it was 1 sample ago, 2 samples ago. The current output, 1 sample ago, 2 samples ago. The current output is that difference equation. If I run that and then display it, there's my square wave. That's my filter's response. Nice thing about digital filters is I can implement complex poles, complex zeros, real zeros. It's actually fairly easy to implement pretty much any filter. What slows me down, though, is the plotting routine. So that's why I collect 500 data points, fill up my buffers, then display it. Once it's displayed, wait 5 seconds, and then repeat. If you get rid of the display routine, I could run the filter continuous and do whatever you want with it. So that's the software version of a high-pass, low-pass, bandpass filter, a digital filter. You can build pretty much whatever you want. So there's kind of your answer. Depends on the sampling rate. Here's what it actually is. Finally, I can control a stepper motor. So with the timer interrupts, I can set the sampling rate very precisely. If I place the stepping inside the interrupt service routine, such as if I want to go forward 1, increase step by 1, backwards 1, decrease by 1, if I'm at where I'm supposed to be, do nothing. By placing that inside the interrupt, the main routine is free to do whatever you want. So for example here, I would have the interrupt every 10 milliseconds. I either move forward, backwards, or do nothing. Then use a lookup table to say where I'm supposed to be. And what that table does is, count mod 4. If I'm at step 0, 1, 2, 3, or 4, is using full stepping. Define which pins should be output. So in summary, the Pi Pico is capable of timer interrupts. With timer interrupts, I can measure time. I can set a fixed sampling rate. I can trigger an event and seconds in the future. Again, interrupts are kind of confusing. However, if you can figure them out, some programs become much simpler to write. And that is lecture number 17 for ECE476.